It can be said that calculus is the mathematics of change. And for a world that's constantly changing, that's a pretty important tool to have. In this lesson, we're going to jump right in and introduce one of the two big concepts of calculus, the derivative. You may have heard the recommendation that, on average, humans need about 2,000 calories per day in order to get enough energy and nutrients. But have you ever wondered where that figure comes from? Well, it turns out there's an interesting relationship between the mass of an animal and how many calories it needs to consume per day on average. It's called Kleibers Law, named for Swiss biologist Max Kleiber. And it says that the daily caloric intake of an animal is proportional to its mass raised to the 3/4 power. Now that constant proportionality, K, does depend on what kind of animals we're looking at, as well as what units of measurement we're using. For example, if we look at mammals and use pounds for mass, the constant is 42. So for example, a cat that weighs 9 pounds would need a bit over 200 calories per day, while a tiger that weighs 400 pounds would need almost 4,000 calories per day. That's a lot of food. Now, one thing about mass and weight that many of us know is that it's constantly changing. So we might ask the question, if an animal's mass changes, how much of an effect does that have on how many calories it needs to meet its daily requirements? In other words, how sensitive is caloric intake to changes in the mass? Let's think about our 9-pound cat, and suppose it gains an extra half a pound. Then it turns out it would need about 9 more calories per day. Now, if we compare these two changes by looking at their ratio, change in calories over change in mass, we end up getting about 18.064 calories per day per pound. What if there's an even smaller change in mass? Say the cat only gains 1/10 of a pound. Well, unsurprisingly, a smaller change in mass will result in a smaller change in caloric intake. But what's interesting is that, again, the ratio between those changes is again about 18 calories per day per pound. Though actually it's a little higher this time. Before it was about 18.064, now it's about 18.16. If we use an even smaller change in mass, like say gaining 1/100th of a pound, that ratio goes up just a bit more to about 18.18 calories per day per pound. Now, in all of those examples, we've looked at what happens if the mass increases. But what if the mass decreases instead? Well, in that case, the caloric intake will also decrease. But once again, if we look at the ratio between those two changes, those two negatives cancel each other out, and we get about 18.19. These numbers seem to be getting closer and closer to something. What might that be? Suppose we have a variable y that's a function f of another variable x. In other words, y depends on x. That's why we usually call x the independent variable and y the dependent variable. When we change the input x, we end up getting a corresponding change in output y. How are those changes related to each other? Well, the key is to look at what happens when those changes get very small, perhaps even infinitely small, or infinitesimal, if you can imagine that. We call those very small changes differentials, and we usually use a lowercase d to represent them, instead of that triangle, which is the uppercase Greek letter delta, which stands for difference. Now, if we look at the ratio between these smaller and smaller changes, the value that ratio settles in on is called the derivative, which we write as dy over dx. The derivative tells us how sensitive a function is to small changes in its input variable. We can visualize the derivative like this. Say we look at the graph of y equals f of x, and we zoom in very close, maybe even infinitely close, to some point on the graph. For many functions, even though the original graph may be curved, if we zoom in close enough, it looks like a straight line. It's what we call locally linear. If we look at the slope of that line, dividing the change in y by the change in x, that's the formula for slope, that ratio is the derivative at that point, which you can think of as the slope of the curve. But since we're looking at a curve, not at a straight line, if we look at a different point, we're going to get a different slope. In other words, the slope depends on where we're looking. It's also a function of x. For that reason, if our original function is f of x, we'll write the derivative as f prime of x. Both of these are valid notations for the derivative, and each one is useful in different situations. Sometimes we even split up the dy over dx and solve for dy to see how these differentials depend on each other. Which is really what sensitivity is all about. How does a small change in y depend on a small change in x? Not to mention, splitting up these differentials can occasionally make calculations a bit cleaner, as we'll see in future lessons. Now, some textbooks are kinda fussy and say you can't treat dy over dx as a fraction. You can't split up the dy and dx like this. And it's true that there's some technicalities at play here that we're kind of sweeping under the rug. But our purpose here is to get an intuitive idea of what's going on. We can always formalize things later. Okay, what do we do about units? Well, again, thinking of the derivative as a ratio, we can use what we know about dimensions. Remember those from last time? And we can split up the units in the fraction. Then, since these differentials are very small changes or differences, they have the same units as the original variables. So we usually read them out loud as the unit of y per the unit of x. So going back to our calories versus mass example, the input is pounds mass and the output is calories per day, so the derivative is measured in calories per day per pound. What that means is for a mammal, like a cat with a mass of 9 pounds, each extra pound would result in an increase of a little over 18 calories per day. Sensitivity is a widely useful interpretation of derivatives, but it's not the only one. In certain situations, it may make sense to interpret the derivative as a rate of change. This is especially true when the independent variable happens to be time. For example, let's say we throw a basketball in the air, and we look at its height as a function of time, say this function right here. Suppose we want to know how fast is the ball rising or falling 1 second after we throw it. Well, like before, one thing we can do is look at what happens over a time interval, say from 1 second to 1.5 seconds. If we divide the change in height by the change in time, we end up getting an average rate of change of -20 feet per second. In other words, the height decreased at an average rate of 20 feet per second during that time interval. But what if we were to calculate the derivative by looking at the ratio of smaller and smaller changes? We'd end up with a snapshot, an instantaneous rate of change of -12 feet per second, which you can and should verify on your own. That says that at t equals 1 second, at that exact moment in time, the height of the ball is decreasing at a rate of 12 feet per second. So that's another way we can think of the derivative, as an instantaneous rate of change. But in situations where a rate of change doesn't make sense, like our calories example earlier, you can always fall back on the idea of sensitivity. A small nudge in one variable is linked to a small nudge in another variable. Both rates and sensitivity encompass the derivative and what calculus is really all about: quantifying change.